Okay, it's 8 o'clock. We will get started. Okay. First thing is like today we are going to move on to chapter 19, the algorithm study. This one actually is a 3 chapter of the algorithm study. We would have one theory study, one chapter in sorting and searching, and one chapter in recursion. So this is actually a very important section. In the past, this 3 chapter or 4 chapter would be designed as a unified algorithm study. But this year's we actually, according to the new framework provided by the College Board, they have 4 units. So right now we are still in the unit 4 data collection. Okay, so as you can see, all of the chapter we are using actually follow the chapters in this AP Computer Science A revised framework for 2026. We pretty much follow it. Okay, so you can see each chapter's topic. If you want to do it, you can. I don't know. In the very beginning, I may have sent you these PDF files, but anyway, it actually just tell you that what would be covered in this class. Okay. Okay, and so we are on the Unit 4 data collection, but this really is the Unit 5 algorithm study. So, okay, that's the first thing that I would like to talk about is this. We enter into 3 chapters of these. And then today is 18, so we will have 18, 25, and November 1st. So we will be finishing APCSA on November 1st. After that, we'll go into competitive programming and APCSB. Okay. But so far, the schedule of this year's user code has not been released yet. Okay. The time has not been released, but usually the first competition is mid-December. Okay, usually it's mid-December. But anyway, we will keep watching. Okay, this part we will keep watching. Okay, and then now we move back to our algorithm study. Number one is why we need to study algorithm. And what is algorithm? Okay, let me see. Let me have someone to talk about it. Kinston, can you tell me what is algorithm and why algorithm is important?
Um, it's like um, an algorithm is like a set of rules or like operations to solve a problem or like a a, a way to problem solve for the computer.
So why is it is important?
Because there are lots of algorithms you can use to maybe um to help you solve a problem. For example, like if you want to like find something, maybe like a I don't know, binary search tree or something.
And why you need to learn algorithm. If you
Because
don't
they're
learn algorithm, what will happen?
because they're really useful because then it's like if you don't learn algorithms every time you want to solve something you have to like reinvent the wheel because if you just learn them in the first place you can utilize them when you actually do need to use them instead of using some like inefficient solution.
Hmm. You know why I'm asking you?
Why?
My question to you, do you know?
Do I know what?
Do you know why I'm asking you this question?
No?
Because when you go to the summer camp interview, they will ask you some question like this. So you need to be prepared that you really understand what is computer science, what is algorithm, what is the benefit of the algorithm, why you study algorithm, and why you actually want to become a master in algorithm. You have to have a whole background scenario and a story to convince the interviewer. Is that
Hmm.
okay?
Hmm.
Okay. Even why you want to study AI, you will have to prepare for those topics. How about Jiang? Jiang, can you talk about what is algorithm?
uh, Set of rules for computers that can be used to like run a specific task or complete.
So if you don't have algorithm, is that okay?
No, because like algorithms like the drawing of the computer actions. So like and we need to learn algorithms because there are like many ways to code algorithm for a single solution, and then it can be really efficient or really inefficient.
Can you tell me some of the algorithm that you know?
I think the most like first algorithm that I learned was to find a missing number from 1 to like 1,000. And then the really inefficient way was to like make a list of 1,000 numbers and remove one by one. But the most efficient one was to like sum it up.
Okay, so efficiency is a very important factor, right?
Yeah.
How about Harrison? Harrison, can you talk about what is algorithm and why you want to study algorithm?
Algorithm is like the process of like calculations done like either by like, a human or like most commonly like a computer. Like a set of like process or like algorithm done by a computer to solve like a problem. And
Mm,
it's like useful because it can also be applied to like daily life scenarios. And like while taking like a test, there's no like time to like come up with new algorithms, so you have to like memorize those equations beforehand.
Okay, all cover very similar topic and point. That's fine, okay? Why am I asking all of you this question is because that later when you become more advanced programmer and computer scientist, you are not only required to do solving problem, but you also need to be able to demonstrate your work and also need to show how important your work is. So you must be prepare yourself so that you'll be able to sell your own product, your own algorithm, your own AI models. Okay, now let's go back to the first question that I asked. What really is an algorithm? So let's go back to the idea of the computer science. So in the first class, actually, I talk about computer science. Okay, computer science. And I say science is the systematical way of studying something. So here, computer science is the science of the computer-related issue, right? So you basically using the computer to solve problems. So basically, computer science target at problem solving, target at the problem solving, okay? So problem solving, you actually want to solve some problems. So right nowadays, we want to have AI, we want to have robot. And then what kind of problem we are solving? Robot, for example, that we have the robot cleaner, robot vacuum, then it will clean up your room. So it solve the problem of clean up the room automatically. So there is a problem that you want to solve. And then the robot can solve this problem. That's problem solving. And for the engineer is to design a machine that can realize this robotic robot so that the robot can move and robot can detect where it is and robot can move and robot can rotate and robot can clean and vacuum. And that's the problem solving. So there are a lot of issues involved in the problem that related to the vacuum cleaning issue, right? So that's a problem solving. So now the third term come in is the algorithm. So computer science is the science to study the computer, using the computer to solve problems. And then computer will solve problem, is used to solve problems. So you study a lot of programming to solve problems. And then there's a term called algorithm. And algorithm is also related to problem solving. But it's not actually one-to-one mapping. It may be many-to-one. So one problem, you may have multiple algorithms that can solve it. Okay. And some of them are good, some of them are bad. Some of them are good in certain situations, some of them are good in certain other situations. Okay, so that's actually so-called algorithm. So algorithm is actually, in another word, is the known solution to the problems. So the target that we want to solve is to solve the problem. Algorithm is a set of the rules or the set of the solutions that can solve those problems. So people already know doing this way, the problem can be solved. And then we call it algorithm. So algorithm is the known solution. So just like your parents may have asked you to memorize the multiplication table, because memorization is the fastest way to calculate the multiplication. Always, table lookup is always the fastest way to solve the multiplication. Even nowadays, you use computer, you don't really solve the problem. You actually can use a table lookup to find the answer. That would be the fastest way to solve the solution. So table lookup is always one way that you can solve problems. So algorithm, there are many different ways to solve the problem, some this way, some that way. So sometimes you can invent a new algorithm. Sometimes you can actually use the algorithm that exists. So the study of the algorithm, basically, there is another issue called the study of the algorithm. So algorithm is the known solution to the problems, and but you may want to study the algorithm. So you need to study the algorithm because of a few reasons. Number one, you may want to know which algorithm is good, which algorithm is bad, which algorithm is fast, which algorithm is slow. That's the efficiency of the algorithm. That's one thing that you want to study. Second, you may want to come up with new algorithm that actually is better. So that actually is a research domain, research that you want to do. And you may also want to look at the algorithm so that your computer says CPU is not enough. I want to use a GPU to solve it. Or should I use an ASIC to solve it? So there is a computing power issue for the algorithm as well. So these are different problems that related to the algorithm, and overall is all one thing called the study of the algorithms, okay? And it's one of the most important topic in computer science. It's one of the most important topic in computer science. So in college, every computer science major, they all have this course called computer algorithms. Okay, so typically in college, there will be a course. Let me show you. So typically, let's look at Berkeley. Berkeley would have Berkeley CS 170. Okay, this one is efficient algorithm and the intractable problem. So there's a course in Berkeley is actually working on this algorithm study for one semester. Okay, and there's another one called let's look at the Irvine. So UC Irvine CS 160. Look at algorithm. Uh, 161. The number is 161. Okay, it actually is called 161. So every university has that, and then There's another course called data structure and the algorithm. So really, this one is easier. This introduction to data structure and algorithm, this one is easier. So from APCSA, next one, you will move on to this one. Okay, that's the next one you will move on. Is this one. And after this one, you go into the algorithm course. Okay, that's where you should be going. And then if you are computer science major, these two courses, DSA, data structure and algorithm, and analysis of algorithm, these two courses actually is the most core course, because whenever you go to interview, these are basically the majority of the problem is related to it. So this chapter is essentially very important. Okay. Okay, let's get started. So in the APCSA, the newer curriculum, actually, we do not see any algorithm study topic, even though there are problems that you may see in the exam, but officially there's no one chapter on this algorithm study. Okay, but in CSP, yes. In CSP, they do have a whole chapter in algorithm complexity, checkable problem, non-checkable problem. So overall, you still need to study, okay? Not because that you don't have the curriculum requirement in the AP. Okay, now let's look at what is algorithm and what is execution time over growth rate and what is the series, the mathematical background, and then big O notation and time complexity. These are the topics we will cover today. So today's course is more math than CS, Okay. So first, we talk about what is algorithm. As we already say, algorithm is a known solution to the problem. So somebody already solved the problem, and then you kind of use the known pattern to solve it. Then it's a known solution. So basically, if you just copy people's solution, that's actually using people's algorithm. But algorithm study at the very high end will need you to invent new algorithms. So the study of algorithm doesn't stop at just studying a lot of algorithm. Studying a lot of algorithm is not the only thing that you will do in the algorithm study, but in fact, you will keep doing trying to find the frontier of the research. Doing AI, large language model, keep moving on to find new algorithms, new computing models to solve problems. And the problem get harder and harder every time. Okay, so that's actually called problem solving. And then the known algorithm, actually in 1960 something, already majority of algorithm already been figured out. So there is a book called The Art of Computer Programming. So this one called The Art of Computer Programming is a book series by Professor Knus and several volumes of it. And then in maybe 1970 something, the majority of the algorithm already been discovered, already been found. So the basic algorithm at that time already been found. So nowadays, if you study some sorting algorithm, I don't think you will get a PhD. That actually already is a well investigated topic. So nowadays, if you want to study algorithm, usually it's from large language model, it's from machine learning, it's actually from AI, from something that actually not just pure a few algorithm study. Okay, it's not so easy now. And this algorithm, since the first day of the computer science, it already been there. And then there's a series of book called The Art of Computer Programming. Okay, most of the computer scientists would have one copy of these. Okay, anyway. So that's actually collecting most of the known solution to the problems. So before we go into the go into the algorithm study. First, we need to know about the process. So the process of the problem solving is the following. First, you need to know about the nature of the problem. Okay, so first you need to know about the nature of the problem. So you got a problem, and then you look at it, you the problem, and you need to understand what they really want you to do, or what they want you to solve, what the problem it really is. So you need to know about the problem there. So you need to know about problem there, and then you actually find a few different solutions. So you find candidate solutions. And those different candidate solutions may be algorithm 1, algorithm 2, algorithm 3, algorithm 4. And then you compare which one actually will solve the problem in the most efficiently and using the hardware resource that you have to perform specific task so that you can solve the problem efficiently. So that's the original study of the computer science for the efficiency of the algorithm. So basically, you need to know about the nature of the problem first, and then you need to find the candidate solutions. Okay, and then based on those candidate solutions, you need to figure out the time efficiency, time complexity, and the memory complexity. So Kingston, why we need to study the time complexity?
Because it tells you about how long it's going to take for an algorithm to run. So like if it's like O of n squared, it's going to take a lot longer than O of n.
No, you can use a stopwatch to measure your computer time. That is actually more accurate if you want to estimate time. So you study the time complexity not because you want to measure the time of your time, how much time you need. So 这样 why we need to study the time complexity?
Because it tells you how the code, like how much calculations the code runs. Tells you how much the code runs the calculation, and then like if it's really high, then it means that it's less efficient.
Yeah, but how can you judge?
Using the big O.
Actually,
Complex.
you talk about the calculation of the time complexity, but you didn't talk about the background incentive or the motivation for study the time complexity. Okay, it's okay. You try. How about Harrison? Harrison, how do you know about why we need to study the time complexity?
So we know like estimate like how long it's gonna take for like if there's like time constraints in like a project.
You also answered a similar way. All of you did not tell the main issue is like, if you want to measure the time for how much time a program need to run, you just measure the time. That's actually easier. You use a stopwatch to measure the time. That's actually easy. Okay, that can solve the problem. That's the most accurate. So time complexity is not measuring the time. It's not. It's not actually just study how much time you will need. No, it's not because that. The main issue we want to study is the scalability. What is scalability? Scalability means that right now the problem only 100 students we solve the problem. So if the scale up to 10,000, what will happen? If it scale up to 100 million, what will happen? So time complexity primarily usually is study the scalability. When the problem scale up, can this algorithm still hold or not? So for example, if you study one algorithm that can only work for 3 students, is that okay? That's actually absolutely fine. Even if it is slow, it is fine. Nobody care because only 3 students example there. You use a very lousy algorithm, that actually is fine. But if you want to study like 3 trillion people problem, then problem scale is too much. So the time that you need to do the CPU you need to buy, a lot of things that you need to allocate a resource into it. You need to study it. That's actually the scalability issue that you want to do. So make sure you understand the word scalability. That's the core that we want to study algorithm, time complexity. Similarly, there is another term called memory complexity. So sometimes the algorithm maybe is very simple, but it will use a lot of memory. So in terms of efficiency, it's good. It actually runs very fast, but it will take a lot of memory. That is, you also need to study memory efficiency. So the same thing, there's also a scalability issue. When the problem go up, can your problem still be solved or not? So you have two things that you want to study, time complexity and memory complexity. So time complexity usually is, you will actually talk about, for example, how many for loop you do, how many plus operation, how many minus operation, how many multiply operation, how many compare less than, greater than operation you do. That based on those counting of the operations, you know about how much complexity you have. And when the problem scale up, when you have the n, it is grow by order of n squared or order of n. We study that not because that this one can predict the time precisely. No, it cannot. It cannot predict the time precisely. But we want to know about when the problem get bigger, will the algorithm still be able to handle or not? So that's the main idea of what we want to study the time complexity. Okay, just because we want to see if the problem is scalable. If you want to really measure how much time, you just do time measurement. You just do time measurement. Okay, and the next one is the memory complexity. So memory complexity, some algorithms use very little memory. So if for example, you use a small watch and iWatch or something, you can actually do computing on it. But those memory hog algorithm, it requires a lot of memory. Then your watch cannot do. You maybe still need to use a desktop computer to run it. So in trade-off of which platform you may be able to run that program, memory capacity also matter. Do you have 1 trillion byte of hard disk? You actually have 20 giga RAM or not? That actually is the memory complexity you want to study. Okay, so if your algorithm require a lot of memory, even though it's very efficient, the performance may drop because you do not have enough memory to support it. Then that's a big problem. So nowadays, the AI, when you talk about the large language model, they do talk about two things: the high bandwidth memory, and also talk about what? Talk about the GPU. How many tokens that can be handled per second? How many flop? How many flip? The so-called floating point operation you can finish in a certain second. That's called the GPU power. At the same time, you also need to have a high bandwidth memory to support your large language model. So algorithm study is not just bound to the time complexity. It's not just order of n. Order of n is one way we study it, but it's not all thing. Okay. There's also memory complexity you need to study. There's also system security you need to study. And a lot of things that you want to study. Okay. Is that okay?
Yeah.
So in a way that actually people study DeepSeek, right? DeepSeek, the model DeepSeek, they do talk about DeepSeek actually consume less power, but eventually their quality of the training is not good. So there's a trade-off. Sometimes the algorithm may be efficient, but they may not deliver the same kind of the quality of some slower algorithm. So it really depends, okay? It really depends. Here, we just give you the idea of what is algorithm and what we want to study in algorithm and what are the things that you may want to know when you study the algorithm. The next one is the what are the algorithm we need to study. So in high school AP level, only sorting, searching, and recursive algorithm. That's it. That's all you need to do. These different algorithm, they only show up in user code. They don't show up in AP level. Okay, so there are a lot of things you need to study, but high school probably only needs and sorting, searching. Okay, that's a problem that you want to solve. Usually that's covered in high school. And then prime number algorithm, GCD algorithm, only those kind of the linear algorithm will be covered in AP level. Then you need to study. Okay, so in college you will go into more and more problem domain. And here you need to study the big O notation, NP completeness. Okay, these two concepts you need to learn. We will talk about it today. So that will be used for type algorithm efficiency analysis. Okay. And then data structure, you need to study data structure to understand the memory complexity, how much memory required by the data structure. Okay, so data structure and algorithm is one base course. After CS, AP, CS, A, and B, you go to DSA, this is level 3 programming. And then later you go into algorithm study. Okay. Okay, that's actually what we want to study today. So basically limited ourselves to very simple problem. Now, first thing is that we want to measure the performance of the algorithm. One way to measure is to do the execution time. And another one is to study the growth rate. So the most accurate thing is the execution time. You just use a stopwatch to measure how much time your program takes. So there are two problems in here. So Kingston, why measuring the execution time is not good?
Because wait,
It is most accurate because you just know how much time it is. But why study algorithm, we cannot just depending on the stopwatch to run the execution time.
like because it like the execution time is going to change depending on what you give the algorithm.
Okay, so it's algorithm dependent. Yeah, but even that we want to study the efficiency of the algorithm. What else?
Can I say
Yeah, Jiang, go ahead.
changes on the runtime? Because like the CPU and the memory state may be different.
Yes,
And
yes, execution time is very much hardware dependent. So if you do like AI, you have the H20, the reduced version for China, that's very slow. You may have H200, you may have the GB200, right? So those are different versions of the hardware and they do different time. So execution time is, you can only study algorithm if you use the same machine, same situation, same setup to run two programs. Then you may claim that. But if you do have different hardware, the execution time is not accurate, not very able to predict the performance. That's number one. The first problem is hardware dependent and system dependent. Second problem is also the scalability. You cannot study the scalability. When the problem goes up, you don't know about how this algorithm will perform because there's no prediction on scalability. So this one is one way to do the efficiency study, but not the only way. Second one, we look at the growth rate. Growth rate is the order n that you are familiar with, how much it grows. This one, not accurate because order n, order 2, n divided by 2. How can these two be the same? These two is not the same. but in terms of growth rate, they are considered to be the same order. Okay, so the purpose of the growth rate is not accurately predicting your algorithm efficiency, but to study the scalability. Okay, key point to study when your problem n goes up, can your problem still handle it or not? Okay, so keep in mind your execution time growth rate. Both can be used for memory complexity. Okay, the third one is a memory complexity. So sometimes you use a TNMNT is a time complexity function. For example, like how many plus sign, how many times you need to have that you would calculate the time complexity based on the function of how many operator of these you will use. And memory is like how many array you use. So you know about how when n goes up, how much memory, how many bytes of the memory may be needed. So these are two functions that you use when you study in the growth rate. Okay, why study algorithm? We talk about it already. Now, before we go into the review of whatever math, before we go into that, let's look at one example. I'm bringing up my project, okay? My computer is a little bit slow. A little bit slow today. Okay, let me create a new project. So the first thing I would like to study is the Fibonacci sequence, okay? Okay, so now first one, we would like to study the Fibonacci. The nature of the Fibonacci function, we don't want to repeat it, okay? We don't want to repeat it because we may study it some other time, but let's just write a recursive Fibonacci function. These two actually you can change to this, okay? So one statement is enough. Okay, the Fibonacci sequence. Fibonacci sequence you have F0 equals 0, F1 equals 1, F2 equals F1 plus F0. F3 equals F2 plus F1. So f of n will be equal to f of n minus 1 plus f of n minus 2. Is that okay so far?
Yeah.
Okay, we just talk about this. Okay, we just talk about this. This is a algorithm that we want to study. And in fact, if you do want to know about the first 300 Fibonacci numbers, they do have the first 300 Fibonacci number on internet that you can search. Okay, so F0 equals 0, F1 equals 1. So somebody already calculated. Okay, so here you can look at the number to the first 300 of them. Is that okay so far? Hello?
Yeah.
Yeah.
So this one, apparently, as you look at the number, this number actually grow by exponential growth. It really grow very fast, okay? But that's not what we want to study right here, okay? That's not what we worry about right here. Let's actually look at the time right now. So first one, we do have this Fibonacci function, and we want to measure the time. So let's look at the time measurement. So let's look at the time measurement. Okay, so we want to do a Fibonacci function, and we want to look at how much time it would take. So we will do first one, we would have a timestamp, so long stem 0, the starting time. Okay, let's actually call it starting time. So let's call start time will be equal to system that current time in minutes. Okay, so let's actually just print this one out so far. I think I may have spelled it wrong, but let's actually print it out first. So this is a function we will use. I think I misspelled something here. Maybe no E. That's wrong. Okay, no, that's actually, let me try, okay? So this one called current time minutes. Lowercase current, okay, I'm sorry. The system that lowercase current, so this one is lowercase c. Okay, so this one, okay, let's actually print out the start. Okay. So this one will measure a timestamp in long long integer format. Okay, and this long integer format means that it is a timestamp, and this timestamp is the Unix epoch time. So what is Unix epoch time? Unix epoch time means that it is based on what? Based on the year January 1st, 1970. And then 12 a.m. in the 0 time in the morning, we call it timestamp 0. And then after that, because this timestamp function is in milliseconds, so it will tell you how many milliseconds have passed since then. Is that okay? Hello?
Yes. Yeah.
So this one, you know about the timestamp in as a long integer. Okay, now let's actually do this. we do have this, and then we do run Fibonacci function. We want to know about the efficiency, so we need to put the time before it and after it. So that's called the Fibonacci function. We don't need the result. I don't care about the result of the Fibonacci function. So let's do Fibonacci function of 40. And then we actually would measure the time again. We will take the time again. This one we will take a time called end. So this one we have time beginning and end. Okay, so we know how much time it takes. So the time that you take will be equal to, let's actually do seconds. So it will be equal to, let's actually don't use a integer, let's use a floating point because you may not, let's use double because you may have fractional part. So this one doesn't have using the n, the minus star divided by 1000.0. So that actually convert from millisecond, convert from milliseconds to second. Is okay?
Yes.
So after that, you can type out this one. So this is the way to measure time, okay? So you say it takes 0.44 f seconds slash n and then SECS. Okay. So this one you take so much time. And let's see. Okay, so it take 2.39 seconds. Now, let me change. So this is a way that you can measure the time for your algorithm. Okay, let's actually do one thing. So let's do this. For integer I equals 0, I less than 40, I increase. So that's print things out now. Okay, so this one will print now this, and then after that, let's actually print an empty line. Okay, as you can see, this time it actually is faster. So it really depends on how much work your computer has. So let's run one more time. So beginning it go very fast and then it slow down. It slow down. Let's actually go to 45, not 40. Let's go to 45. So slow down now. It's actually take longer now. Take longer now, even longer now. Even longer now. Okay. Okay, so Kingston, do you have comment on the time? So far, the time that you see.
It's significantly longer.
It's longer, yeah, but how much longer you can expect?
What do you mean?
So F444 and compared to F43, how much more time you need to take?
Like just a few more seconds.
Hmm?
Like just a few more seconds.
No. May not be a few seconds. Let's actually increase the number, continue to increase the number. Let's increase to 48. Y. It slow down. That's one thing that you will observe. But second, you will know that the time is not growing linearly, not growing one by one. It is growing exponentially. And why it is growing exponentially? So, why this one will grow exponentially? You see 45 already slowed down. I haven't seen the 46 yet. 46 will take a long time to get a 46. And then 47 will even longer.
Because it recalculates the whole thing again instead of using the number again.
Yeah. So it actually, when you do Fibonacci of 2, it is equal to Fibonacci of 1 plus Fibonacci of 0. So basically, if we look at the time complexity, Fibonacci of 0 plus Fibonacci of the 1 roughly equals to calculating the Fibonacci of 2. So either way, Fibonacci of 45 will be equal to the Fibonacci times of the 44 plus Fibonacci time of the 43. So basically, the time spent on these two numbers will be the same as the 45. So 46 will be the sum of the 44 and 44. So basically, the time grow exponentially. Even right now, we haven't seen the 47 yet. We still haven't seen yet. So this algorithm, when the number grows up, it actually doesn't work. It almost is dead. Okay, so this is time measurement number one. We talk about time measurement. Second, the Fibonacci function right now using this recursive algorithm actually is exponential time. Okay, and this one is a top-down design. Okay, top-down design. So you see right now, okay, 47, another bad things happen. It actually become negative. So Harrison, why this one become negative?
Because did it go out of like integer bit limit?
Yeah, it actually overflow. The number of bit is not enough. So you need to change the integer to long or even to long integer, okay, to big integer to handle it. So that's actually a different story. So we don't study it right now, okay? So right now, this using this return type integer is wrong. Some problem you cannot just return integer. You have to use different thing. Right here, what we study is this algorithm actually when it grow, your time complexity of the n will be equals to time complexity of n minus 1 plus time complexity of n minus 2. So this one is really too efficient, too slow. So can we speed up? Yes, you can speed up. Okay, you can speed up. Let's look at another one. So let's look at the Fibonacci 2. Okay, let's create another one called Fibonacci 2. So that green number, I'm not going to solve it right now, okay? It's actually too much for us. Let's actually copy this Fibonacci function. Let's put it over here. Let's delete this part. Let's rewrite this Fibonacci function. We don't really do this. So if n equals 0, n equals 1, we actually return n. This part is still okay. Now let's don't do this recursion now. Don't do this recursion. Let's actually look at the problem. So your f F0 equals 0, F1 equals 1, F2 equals F1 plus F0, F3 equals F2 plus F1. So we can basically use a CVO function to solve the problem. Okay. So let's do this. Let's do integer f equals, let's see, 0. Okay. Integer I equals 2. Okay. And then while I less than equals n, we do the following thing. When we are done, we will return the Fibonacci number. Okay. So right here we would have integer f1 equals 1. This is Fibonacci 0, Fibonacci 1 is f n minus 1. Integer f2 equals 0. This one is Fibonacci 0. Is f of n minus 2. So right here we get these different numbers. So we say our f2 would be equal to our f would be equal to f1 plus f2. Okay, and your f1 would be equal your f2. Your f2 would be, I'm sorry, your f1 would be your current f for the next row. F2 would be your, no, you should do f1 first. So let's do f1, your f2 will be equal to your f1 first. And your f1 will be equal to your f. This is for the next row. Okay, let's start it. So your f2 equals f1 plus f0. So this is f1. This one is f2. Okay, this is f2, f1, f. So f3 equals f2 plus f1. So basically you push this one to here, push this one to here. Your f will become your f1. Okay, your f1 become your f2. Next round is f2. Okay, is that okay?
Yeah.
So this one, if we run like 47 times, how much time it will take? It actually is only 47 times 3. This one is a linear algorithm. This one is an order n algorithm. Let's see. Step 2, let's see. I forget to put I increase. Sorry, I forget to put the I increase. Every time I need to increase by 1, okay? Okay, it gets the same result that you need, but it's way faster, way faster. This recursive is actually take a long time to finish. And this one is recursion. This one is one while loop, order n algorithm. So this, I give you this example to show you what time measurement is one way that you can study the algorithm. Yes, it's actually a very effective way to study. But because you want to study the scalability, when your problem goes up, you really need to learn how n behave, how the number behave. So a algorithm, actually, when in a textbook, they usually teach you this Fibonacci function using recursion. But this one actually in the real world, nobody use this one. Actually, nobody use this algorithm. It's actually a algorithm for toy, not really practical algorithm. Nobody would do this. In fact, when people really do Fibonacci calculation, I would suggest to use this one. Just a while loop doing n times is an order n algorithm to finish it. Compared to the other one that's order 2 to the power n, is way slower, way faster. Is that okay?
Yes.
This one just 3 operators, 4 operators. That's even this one considered is 4. So you actually is actually 4 times 47. That's it. It's an order n 4n algorithm. Even if you count every process assignment. Okay, so this one way faster. So the textbook just want you to study what's recursion, but they don't tell you that the recursive algorithm for Fibonacci is of no use. So when you solve a problem, you actually take that approach or this approach. That really depends on how you actually solve the problem. Okay, while loop sometimes perform much better than the recursion, but not always. Not always. Sometimes while loop is very difficult to write. Recursive is easier to write. Okay, so there are different things that you need to look at. But right here, we just tell you, based on this example, to tell you the necessity of studying algorithm and how you need to study it, and what is the time complexity and its relationship with growth rate. Okay, that's what we want to demonstrate. Next one, we'll go into the review of the math. Now, we want to calculate the number of operator needed. How many S, how many minus, how many multiplication, how many comparison. And will this be tested in AP? Yes, it will be tested in AP, okay? It will be tested in AP. First one, you need to know about the summation, big sigma notation. Okay, big sigma notation. So Harrison, what is this later? Have you seen this before?
It's like sum of, right?
Yeah. So why they choose this later?
I don't know like the origin, but I know it's like a Greek letter, like sigma.
Yeah, but Greek letter sigma means what?
Like the sum of like values.
It actually is a capital letter of the S.
Uh,
So it means sum. So they have two things, one above and one under. So when you do sum of the k equals 1 to n, means the k run from 1 to n for all k. Okay? Okay, so this is the what we want to study. Now, the simple things that actually very simple thing that first thing that we want to do is that, for example, if you have 1 plus 1 plus 1 plus 1 plus 1, and then going for n of the 1, so it totally become n times 1. So it will be n. Okay, so you have C plus C plus C plus C plus C for n times. This one would be n times C. Okay, so in math, we write this summation of the C n coming from 1, I'm sorry, k coming from 1 to n. Then the answer will be n times C. It's okay?
Yeah.
Okay, so this is n times c. Now the next one is if you do 1 plus 2 plus 3 plus 4 plus 5 up to n, what would be this result? John, how much is this one?
What do you mean how much?
What is the sum of these?
1 to
1
3.
plus 2 plus 3 plus 4 plus 2n.
Sigma n.
Sigma k from 1 to
0
n, and then
to
equals what?
what do you mean equals what?
This is must have a formula. What's the formula?
I don't know.
You don't know. How about Kingston? What's the formula?
It's the first one plus the last one, and then you multiply by the number of elements divided by 2.
So what's that?
N times it's n times n plus 1 plus 1 divided by 2.
Okay, this actually is a seventh grade math. You need to remember. Okay, this one is this. A way to prove it is you have 1 plus 2 plus 3 plus blah 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 plus n. You reverse it, you become n plus n minus 1 plus n minus 2 plus blah 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 plus 1. These two sum together. Left hand side is 2s. If one of these is s, you reverse it, so it's actually another s. So s plus s it becomes 2s. 2s will be equal to each one of these is n plus 1. Totally, you have n of them. So your s would be n times n plus 1 divided by 2. This is a standard things that you need to remember. Okay, sum of 1 to n is this. You have to remember. So if you say n is 10, it will be 55. You must have the answer right away. Okay? Is that okay?
Yeah.
These are very basic things. Should be common sense now. Now, that's that. How about if I have a number 2 plus 4 plus 6 plus 8 plus blah 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 plus up to 2n? What is this sum? Harrison, what would be this sum?
Is it just n times n plus 1?
Yeah. It actually is a summation of 2k, k from 1 to n. Take these 2 out. So it actually is a 2 times summation of k from 1 to n. So it's the 2 times n plus 1 divided by 2. These 2 cancel out. So it's like that. Okay, good. Now next one we have next one, let's do one plus 3 plus 5 plus 7 plus blah blah plus 2. 2n plus 1. All the R number sum. So Kingston, how to solve this problem?
It's the same, but you do 2n plus 1 plus 1 multiplied by and 2n plus 1 divided by 2 divided by 2. Because
No,
you
it's
just
not.
divide like
It's not the same. It's not the same. It's actually you have 2k plus 1. Okay, let's actually adjust. Let's change this one to minus. Okay. Because we want to use a k from 1 to n. Okay, so summation of 2k minus 1. Here you should have k equals 1 to n. This whole thing will becomes summation of k equals 1 to n 2k minus summation of k equals 1. Here you have 1, here is n. So this whole thing is n. This whole thing is n times n plus 1. This minus this one, you get n squared. So this thing eventually become n squared. So what I'm going to teach you right now is not just is a systematical math that you can basically calculate all kind of this kind of a digital sequence. And study this digital sequence will give you the idea, number series will give you the idea of the complexity of the algorithm. Is that okay? Otherwise, how can you calculate your complexity of the algorithm? You have to have the math to help you to study. Okay, I know most of you may not know this math, but that's not okay. That actually, the kind of math that I'm talking about right here, when I was little, I studied in middle school. Okay, this one is pretty easy. Pretty easy sum. Next one, let's assume that we want to sum up 1 square plus 2 square plus 3 square plus 4 square plus 5 square plus 2 n square. How much is this one? How to solve this one? Anybody has idea?
geometric sequence. Geometric sequence.
What kind of geometric sequence? Is 1 square plus 2 square plus 3 square? It's not geometric sequence, no. Plus 3 square plus 4 square plus 5 square plus n square. The answer is you will have a formula of n plus 1 cube will be equal to n cube plus 3n square plus 3n plus 1. Is that okay? Is that okay?
Yeah.
So 2 to the power 3 equals n is 1, 1 plus 1. So 1 cube plus 3 times 1 square plus 3 times 1 plus 1. 3 square cube, I'm sorry, 3 cube will be equal to 2 cube plus 3, this is 3. 3 times 2 square plus 3 times 2 plus 1. Continue. continue, you have n plus 1 cube equal to n cube plus 3 times n squared plus 3 times n plus 1. Sum the whole thing together. Sum the whole thing together. Sum the whole thing together, your right side and left side will cancel out these. Cancel out. Because your left side have this, right side have this, it will cancel out. So eventually your left side becomes n plus 1 3 cube equal to 1 cube plus 3 times summation n squared plus 3 times summation n plus totally this one is n. So here is n plus 1. So the thing that you want to find, the summation of n squared is right here. So 3s plus 3 summation n plus n plus 1 will be equal to n plus 1 cube. So 3s will be equal to, move this to this side, so it will be n plus 1 cube minus n plus 1 minus, you minus this one, minus this one, minus 1, 3 times summation n. And by doing this, you will solve the s. S by dividing this one to 3. So s will be equal to 3 n plus 1 2n plus 1. So there's an equation that you can figure out. Okay, this one will give you the summation of n squared. So when you need to calculate all of the summation of n squared, this is the formula that you find the summation of n squared. Why am I doing this for you? Because I want to teach you, this is the big summation mass, discrete mass, big summation mass to teach you how to estimate the complexity of the algorithm. Now you need to study this. So that's the formula that I say eventually become, oh, I'm sorry, here is 6, not 3. Eventually is this one. N times n plus 1 times 2n plus 1 divided by 6. So this is summation of n squared and n cubed. And you can continue to derive n fourths and fifths. Whatever over, you can all do it. So basically that will give you any polynomial function of the n, you will be able to solve it. Is that okay?
Yeah.
So as long as your function is a polynomial of some kind, you should be able to figure out the complexity. So this one is the first summation of k, you get this. And then there's and then they will calculate the summation of n squared is right here, okay? And this math can be used for a lot of different kind of discrete math, okay? So here I'm just giving you the basic idea of how to do this. And this is a whole bunch of the discrete math you need to learn to solve, okay? Whatever, here we do have give you the examples. Okay, so there is a generalization form, so you can go to the any of the summation k to the power a, you will be able to solve it. So any of the polynomial term, we call it Fujita formula. Okay, whatever, Fujita. This one can solve it. Okay, whatever. Okay, I think that just give you the idea of how this complexity being handled, but we don't go even further now, not too much, up to here, okay, up to here. So now you actually count the number of plus minus sign. So you know about your time complexity and you can estimate them by summing up the total operation that you get. So you use a big summation to solve it. That actually is fine. Okay. Okay. Other than the big summation, there's another symbol you also need to learn. There's another symbol you also need to learn. Okay, that's actually called pi. So you pi for k from 1 to n for k. This one means 1 times 2 times 3 times 4 times up to n. So this sigma is the sum because it's the big capital letter of the S in Greek letter. This pi is product. It's multiplication. It's actually the capital letter of P in Greek letters. So product of 1 times 2 times 3 times 4 to n is called pi function. Is that okay? Hello, is that okay?
Yeah.
Here we don't study pi function, okay, too much for you, but just let you know they are a branch of math to do that. Okay, next one we will go into the big O notation. Big O notation is to based on the calculation that you found. Okay, you do some summation and you figure out time complexity is such a n function, n squared plus 2n plus n, whatever function you have. Then you will start to look at the big O notation. So here we will talk about big O notation. Big O notation, you need to know about big O function and T function and omega function. These three functions you need to know. So time complexity is like this, is a T function. So it's upper bound, we call it big O function. Lower bound, we call it this omega function. Okay, I mean small omega function. Upper bound we call it big omega function, and the growth rate we call it big O notation. So these 3, 4 things are actually different in terms of big mass. Okay. So T of n is the number of steps take or to do a problem that actually go like this. Okay, and then there are worst case and average case and base case situation. Okay. So Harrison, we have a linear algorithm. We want to find a number with the value of the key in an array. So this one, the key may, and then you need to return the index. So this one, best case, how much time it take?
1.
One, the first one you find, okay? Worst case,
The 10th one, the like last one, like
you
the 10th.
didn't find it, so it's order of n, right? So this one
Yeah.
is 1, this one's n. How about average?
N divided by 2.
N divided by 2. So these are the 3 cases study. Same thing for any algorithm, we also have the study of this, okay? You need to figure out what is the scenario that will make your best case happen and worst case happen and average case happen, okay? So Kirsten, best case, worst case, and average case, which one the most important?
The worst case,
Why?
because you want to minimize the worst case because it's the one that, I don't know, like,
Worst case is correct, but your reason, your rationale is not there yet. You did not provide a good reason for it. How about John? What is why we want to look at the worst case more?
Because like in some algorithms, the worst case, like the best case and the worst case can have like a not much difference, and we want to see
Because worst case is your bottleneck, right?
yeah.
So let's assume that you search the internet and your web page, you want to have some response. So the response time, how much time you need to wait for the web page to come back? That is the worst case. That is not the best case or average case. Because what best case you show up right away. Average case you may spend 1 second to show up right away. You don't care about that. But if you submit some job and then you wait for 5 minutes, you still don't get it, then you consider the website is down. Not because the worst case doesn't match you. Maybe it's still computing, but you may consider that computer maybe is down. So worst case is important because we care about the response time. Okay, when we talk about delay, we want to know how much delay it would take. So usually worst case is what we will study, but sometimes average case is okay. For example, if your average case is 99.99999% of the cases, everybody will perform that worst average case. But worst case only happen in 0.00000, very rare cases will happen. You may not worry about it. You know what I'm saying? So yes, most of the time we care about the worst case more, but not always. It depends. In practical use, some of the worst case may be ignored. We just consider it's dead. Then we restart the machine again. Is that okay? Hello?
Yeah.
In that case, we call it an ad hoc algorithm. We may just want to get a approximation solution. And then you need to estimate its complexity. So you got the time complexity function and you actually ignore the marquantitative constants. So 100 n divided by 2, same thing, we call it order of n. Order of 5 is also order of 1. Okay, so we all actually ignore all the multiplicative constant. We also ignore the non-dominative terms. So if we have an order of a n squared plus b n plus c, then we will ignore c constant. We will ignore n. We will keep this one only. So it's the order of a n squared, but we will drop the a as well. So it's actually just order of n squared. Okay. Is that okay so far?
Yeah.
Okay, constant time, we talk about it. Now, determine the big O notation. So that's actually here you have different growth function, growth order of 1, order of log n, order of n, order of n log n, order of n square, order of n cube, order of n square, 2 to the power square. So usually when you go to the competitive programming, they require of time less than order n log n. Anything greater than here, usually in competitive programming doesn't work. But there's a technical term called trackable time that your computer is able to track it. Is using polynomial time. If your function can be expressed in the polynomial function, then we say it's a trackable problem. Okay? So trackable problem doesn't mean it's efficient. It just means that you may find the machine to solve it at a reasonable time. Efficient algorithm usually using time of log order n log n or lower. Is that okay?
Yes.
And usually exponential time considered to be bad, or sometimes we call it NP complete, non-polynomial time complete. Okay, you cannot finish it in polynomial time. So basically, when you study this, you actually first set up the time complexity function, study it, and then look at its growth rate. Okay, so first one, we have a repetition, simple loop. So we do for I equals 1, I less than equals n. Okay, this one, Harrison, how much time needed for this one? Growth rate for this one?
Wait, what do you mean?
Well, how to say this one's order of what?
Like n plus 5.
No, it's not n plus 5. No.
No, it's in 5 times n.
This one is not 5. There's no 5. This is a constant 5. It's not 5. This actually one operation is, that's assumed is time c. So you do n times, so you total times n times c is the order of n times c, and it will be order of n. So this one, the answer is order of n. This whole thing is constant time. It's nothing to do with 5. It's just a constant time, maybe 2 seconds, maybe 1.1 millisecond, something like that. So one operation time, that's c, totally you take this n times. So it's order of this. Is that okay so far?
Yeah.
This one for Jiang, how much will this time will take?
Big O n square.
Yeah, this one n by n, so it's actually very apparent. Okay. This one, Kirsten, how much this one will be?
Um,
Uh,
oh, N I
This one you will have first one, I equals 1, you run 1 times. 1, and then second one you have 1 and 2. So 1, 2, and then 1, 2, 3, and then 1, 2, 3, 4, and then up to 1 to n if I equals n. So summation of this is
Uh,
hello?
n square.
Hmm?
N square.
9 squared, you have 1 plus 2 plus 3 plus 4 plus 2n. What's the number?
that's n times n plus 1 divided by 2.
Is order of this. Then we drop the
So it's of n squared.
drop this one, so it's actually order of n squared. But before you answer that, you need to say it's order of n times n plus 1 divided by 2. This is the complexity that you come up with. Okay?
Mm.
This part you still need to spend more time to study different algorithms, okay? Otherwise, you have to estimate the growth rate very quick to determine which one you will use. This one for Jiang. How about this one?
I think you consider this as n on
So
big O.
how is the total time complexity?
Big O n.
I mean the time complexity.
Oh, 20 n.
This one is assuming the time for the inner operation is 1c time. So this whole thing is 20c. 20c, each one would run for n times. So n times 20c. So it's the order of n times 20c, but this constant will be dropped. So it's the order of n. Okay? This one for Harris. This one you have 1 for loop, 2 for loop.
Wait, is it like the first one is order of n, right?
The first one is not order of n. No.
Oh, no, order of it's like I don't like really get it.
You don't really get it because you don't pay attention enough to hear. This one run 10 times, each one is c time, so it's a 10c time. This one 20c for n, so it is n times 20c. These two sum together because you run this one first and then run this one. So the total complexity is like this. Order of these, this one not significant, so drop. This one not significant, drop. So it's the order of n. But its dominating factor is this one.
Okay.
You cannot wait until I tell you what it is to be able to solve the problem. Then you are out already. You cannot do competitive programming. You know what I'm saying?
Yeah.
If you really want to go for the computer science, you cannot do this. That's not enough. Hear me, everyone?
Yeah.
You need to be active, trying to solve the problem by yourself, not waiting until people feeding you something. That's too late already. Okay? This one, let me have Jiang this one. So previous one is a sequential. That means that you have task A followed by task B. So the complexity is the sum of task A plus task B's complexity, and then the dominating one take over. Okay, that's when you have a sequence. Next one, we do have another one that's actually is the selection. Selection means that you come to here, you go right side or you go left side. So right side, let's assume this is task A, this is task B. So in terms of this, how can we determine the complexity? So for Jiang, how can we determine this one?
Task A is like C if we define the complexity as C.
Mhm.
And in else statement, then the complexity will be list length times the complexity for printing out T.
You are trying, but not exactly. How about Kingston? You talk about it.
Like you just calculate the complexity for both and keep the largest the largest one.
Yeah. This one, the key point is you have the A branch and B branch, two branches. So it's a maximum of the two. The complexity of A and complexity of B. So right here, you cannot just say, oh, let me do sum. No. You actually, you do selection on right or left. And which one is the dominating factor? The bigger one is the maximum of the two is. Okay, now that's the top level. You top level, you go this one or this one. But A, how much time needed? And B, how much time needed? More detail now. So Harrison, how much time? How much complexity this A should be?
A should be list.length, right?
How much time complexity?
Order of n.
Yeah, this one's order. Be careful. This one is a function, but a function burn order of n. You cannot say this is order of one. No, it's one function, but it really take order of n. When your number of element grows up, it will take longer time. So you cannot say this is the order of one. It's not order of one. It's a one function, but you go into there, it's actually it's a for loop there. You do not see it. Okay. This one is also a for loop. So both of them are order of n. So the maximum of it is the order of n. Okay. Okay, anyway, here we go through the sequential, selective, and loop, and nested loop, and give you the idea and give you the function of summing up everything, okay? So when you later go into some tougher problem, you should be able to study, okay? Next one, we are going to study an example and study the complexity of the Tower of Hanoi. Okay, let's look at the Tower of Hanoi. So Tower of Hanoi is you want to move, let's assume that you want to move all the disks from A to B. Okay, so what happened is the small one cannot go below the top one, okay, the big one. So right here, you actually need to move this one, you need to move this forward to here before your big one move to here, and then your top four move back to here. So that's the algorithm. This is how Tower of Hanoi is. Okay, now we want to figure out the complexity of this Tower of Hanoi. So let's look at this video. Can you hear it?
Hello, this is the puzzle guy, and today I have
Yes or no?
a puzzle
Yeah.
which
Yes.
was invented in 1883 by French mathematician. And the name of this puzzle is Tower of Hanoi. As you can see, it's made out of wood. It has 3 pegs and 8 discs. Sometimes you can find different version of this puzzle with 7 discs or 9 discs. And the goal of this puzzle is to move all discs from one peg to any other. And there are only 2 rules on this puzzle. The first one, you have to move only 1 disc at a time. And the second rule is that you can't put bigger disc on a small one. So this move is wrong, and this one is wrong as well. There are many different methods of solving this puzzle. Some of them are pretty difficult to understand, but I have one very simple method how to solve it, and I'm going to show it to you after a spoiler break. If you want to see the solution of this puzzle, you can keep watching the video. But if you don't want to spoil all the fun trying to solve this puzzle by yourself, stop watching now. To show you my solution, I will start with only 3 discs. So, for example, if we want to move all 3 discs on other peg, what you have to do is just to make one move, then another, and then what you have to do is to take the small disc, put it on top of the second, now the big one, now put the small disc on the first peg, the second disc in the middle, and put the first one on top. So that's how I moved 3 discs from one peg to another. I don't know if you
Okay, so far okay?
Yeah.
Yeah.
Okay, let's look at it, okay? Let's look at it. We will analyze the case. So they are basically, let's assume that you have 3 posts. There's A, B, C, 3 posts. So what you want to do is that let's assume that we are still doing 3 discs. So your 3 discs, what you want to do is you move from A to B. But there is a spare one called C that you can use. So let's assume this is 3 discs. So let's call it Hanoi of the 3. So Hanoi of the 3 are from A to B. So that's actually, let me use typing, okay? This one actually very ugly. Let me do typing. So it's actually Hanoi of 3 is moving from A to B. It will be equal to, you move the 2 discs to C. So you would actually equal to Hanoi of 2 from A to C, okay, plus a Hanoi of 1 disc from A to B. And then plus a Hanoi of 2 discs from C back to B. Is that okay so far?
Yeah.
So this is the recursion that it has. So this means that you actually moving the 3 disks from A to B, you need to move, you actually have 2 moving disk of 2 and 1 moving disk of 1. Because you need to move 2 disks from A to C, then move the big one from A to B, and then move the C back to B. So it totally this one. So you can look at the complexity is actually H of 3 would be equals to 2 times H of 2 plus H of 1. So H of 4 will be equal to 2 times H of 3 plus H of 2. So H of n will be equals to 2 times H of n minus 1 plus, oh, I'm sorry, this one is H of 1. And H of 1 is 1, okay? You move one disk from one port to the other, which is 1. So this is the complexity function, recursive function we have. Now, what is this function now? Anybody know what is this function? Here, let's start with H1. So 1 disk from 1 is H equals 1. H2 would be equal to 2 times H1 plus 1. So it will be equals 3. Okay? How about H3? So what would be 2 to the this one? So the answer is n disk. You will take 2 to the power of n minus 1. If you continue this mass. It's the same as the binary search function. When we talk about binary search, it's the same mathematical function. Any question?
No.
I know most of you are lost, but here I just give you the idea, okay? I don't expect any one of you understand this. So far this year, I don't see anyone suitable for competitive programming yet. Still too far away. Not working hard enough. This one, we actually derived it before, so we don't repeat it. You can derive it, this one, it actually is equal to, the number is equal to Hn be equal to 2 to the power n minus 1 plus 2 to the power n minus 2 plus blah, 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 up to 1. And this whole thing is equal to 2 to the power n minus 1. Okay, that's it for today. Good night and bye-bye.
Thank you.
Thank you. Bye.